This lesson is on Pascal's principle and hydraulics. Pascal's principle, you may remember, is that the pressure in a fluid depends only on the depth, not on the shape of the container or anything else. Here is an example. We have a small platform on the left, big platform on the right. There's a fluid that fills the entire tube. And let's say we have a car on this side, on the platform, that has a mass of 2,000 kilograms. And if you multiply that by 9.8 meters per second squared to get it in newtons of force, then we'll say that 9.8 is close to 10 to within 1 sig fig. So this has a weight of about 20,000 newtons. One significant figure is good enough for this example. So 20,000 newtons. 2,000 kilograms is over 4,000 pounds. So, I mean, this is a reasonable sized car. All right, so let's figure out how much force do we have to apply over here to lift the 20,000 newtons over here. So we'll say that the force over here on the other platform down, F2, that's the 20,000 Newton weight of the car. And I'll say the area of this platform over here, or at least the area of the tube over here, A1, is 10 square centimeters. So, that'd be a square, 10 centimeters on each side. So not tiny. And then the area over here, area 2, the area of the column of fluid where the other platform is 2 square meters. All right, well, Pascal's principle says that the pressure in that fluid has to be the same as long as the depth is the same. So if I say that these are, in fact, at the same height, then pressure over here has to equal pressure over here. Pascal's principle says P1 equals P2. Well, remember, pressure is force divided by area, force per unit area. So I can say that F1 over A1 equals F2 over A2. F1 is what we're looking for over A1, 10 square centimeters. Well, we've got to convert that to square meters. Right here, 10 square centimeters. We multiply that by 100 centimeters. And because the centimeters are squared, I have to square my conversion factor. So 100 squared is 10 to the 4. 10 times 10 to the minus 4, because the 100 is in the denominator. 10 times 10 to the minus 4 square meters, or 1 times 10 to the minus 3 square meters for A1. So we have F1 over A1 is F1 over 1 times 10 to the minus 3 square meters. And that has to equal F2. F2, we said, was the weight of the car, 20,000 newtons, over A2, and that was given as 2 square meters. I've got square meters in the denominator on both sides, so I can cancel those, and I need to multiply both sides by 10 to the minus 3. So F1 equals 20,000 times 10 to the minus 3. 20,000 is 2 times 10 to the minus, or 2 times 10 to the 4. So 2 times 10 to the 4 times 10 to the minus 3. So when I divide by the 2, that should be 10, or 1 times 10 to the 4, or 10 newtons. So I can lift a 20,000 Newton car, a 4,000 pound car, by applying 10 newtons, or 2.5 pounds. Not very much. Why hydraulics are so useful. Or, you can apply a very large force to your truck's brakes, to your truck's wheels, with a very small force on the truck brake pedal. Got a semi. Okay, does the fact that we can do this bother you any? Aren't we violating some law of conservation of energy or something? How can you lift something that weighs 20,000 newtons with just 10 newtons? Why is this okay? I mean, we're changing the potential energy of something. Potential energy is mgh, right? So I got to worry about the mg. I'm changing the gravitational potential energy of something that weighs 20,000 newtons by changing the potential energy of something that only weighs 10 newtons. How does that not violate conservation of energy? I'll show you. We don't get anything for free. when you push down on the left column, you're going to displace some volume of fluid on the left column. However much volume of fluid you push down in the left column has to go up on the right column, right? Whatever fluid disappears one place, got to appear the other. The volume of fluid on each side, the volume displaced on each side has to be the same. Well, volume, you can think of volume as the area of each column times the height that that column moves when I push it. Those two volumes have to equal each other. So let's see, if I set those equal to each other, let's see what happens. So A1, 10 square centimeters, that was 1 times 10 to the minus 3 square meters. So A1 was 1 times 10 to the minus 3 square meters. H1 equals A2. A2 was given as 2 square meters, H2. So let's say that then H1 equals 2 over 1 times 10 to the minus 3 H2, or H1 equals 2 times 10 to the 3 H2. So for every 1 centimeter I want to raise H2, I have to raise H1 2,000 centimeters. That's why if you ever use a hydraulic jack to like raise your car, to change the tire, you think you're pumping like forever to get the car high enough to change the tire, because, well, you got to do it. I mean, in my particular example, it would be 2,000 times as many pumps on the jack as to raise the car by however much you're pumping. So yes, we can lift 2,000 kilograms with a 1 kilogram weight, but it'll be slow. And as far as brakes are concerned, who cares? I mean, the calipers on your brakes, they can just be a tiny distance away from the brake. So you don't have to move the brake pedal all that far to get them to reach.